Welcome to the Rutgers Cooperative Extension Compost Management School. These video presentations are designed to help you learn the principles of manure composting and the proper utilization of composted manure. In this video, we will hear from Loren Muldowney on assessing compost quality.
Just before I get started, I want to tell you a little bit about working at the soil testing lab. Since we're part of the Cooperative Extension, we have kind of a different relationship with testing than the typical commercial lab, but in particular because we serve homeowners and landscapers and environmental consultants and civil engineers and golf course superintendents and municipal people that are trying to make sports fields and people who are making compost and trying to sell it and people who are blending soil and trying to sell that or trying to buy materials that are blended or manufactured or dug out of a hole someplace. So we have a really diverse set of customers, and our mission at the Cooperative Extension as part of the State University is to serve the public and to provide science-based information without favoring any group over another. So I'm not on anybody's side, except that I like to get accurate information, and that's how I assess my success, is like, did I get the right answer? Whether people like it or not, let the chips fall where they fall. So, and I think that is all works to the favor of people that are producing a good quality product. I want to talk a little bit about representative sampling. It's not very sexy, but it's really important. And the first part of representative sampling happens before the sample comes to our laboratory. And I have no control over that whatsoever. So all I can do is try to make a pitch that representative sampling is important. There are published methods for sampling compost, in particular from windrow situations. One system that comes to mind is along a certain length of windrow. You need to sample from 5 locations. You need to take 1 sample from the exterior, 1 sample from 18 inches inside, and 1 from the center of the pile. Ultimately, you blend all this stuff together as homogeneously as you can make it and bring a subsample to the laboratory. Now, I have a private concern that often the things that we get in the laboratory have not been sampled properly, but I take no responsibility for that. Once the sample arrives in our laboratory, I have to assume that whoever took the sample did it the right way, because if they didn't, there's not a darn thing I can do about it. But the data that we provide is all based on that assumption. Once we have it in our custody, we do our utmost to get representative samples. We typically get a gallon-sized bag, like a Ziploc bag full of compost. Sometimes it arrives via FedEx in refrigerated, packed in dry ice. It depends. Sometimes it's been sitting in the post office box, over the weekend. So people are quite variable in terms of how they handle their materials, and that really depends on what their concerns are. We get compost from home gardeners who are really just kind of curious. They want to see, how am I doing? And honestly, they produce some of the best compost that we get in terms of its extreme stability, freedom from odors and stuff like that. People that are in the business of buying or selling compost, they're usually a little bit more concerned about speeding up the process, about throughput, and they tend to be a little more careful. They get things that are refrigerated and stuff like that. Sampling within the laboratory also, when we get our sample, we do have to fractionate it according to its physical characteristics to some extent, and that's a large chunk of what I'm going to talk about today. And your sampling technique and also the tests you ask for depend on why do you want these data. And that runs the entire spectrum of possibilities too. Some people are concerned with nutrient management. Some people are concerned with regulatory compliance. And they have no idea what any of these tests mean. But all they know is, like, I need numbers on this piece of paper, and you are going to give me those numbers. And it's like, that's fine. If they ask me a question to explain something, I do my best. But people get sampling data, they get laboratory data for different reasons, and we have to respect that. So what is actually tested? We have two compost tests options on our forms. One is called the technical compost battery. Technical compost battery includes moisture, organic matter by the loss on ignition method, pH, electrical conductivity, that's EC, TKN, which is total Kaldol nitrogen, available nitrogen, which we also call inorganic nitrogen, but basically it is soluble nitrogen. It's extracted by water. Maturity index, a visual assessment, which is basically I look at it and write a narrative description of what does this look like to me, and carbon to nitrogen ratio. That's included in our technical compost battery. In the basic compost, there are somewhat fewer of those things. That's typically what a homeowner or a home composter would be interested in. And occasionally people also ask for compost available nutrients, which are water extracted nutrients as listed there, and compost total nutrients, which is we burn to ash the material, get rid of all the organic material, and what's left is dissolved in acid. So that's basically everything that's in there. It's not what's going to be extracted in an agronomic sense. Here we have the output of the process, our test report. Okay? In comes a bag of compost and out goes that piece of paper, which you can get by email, by mail, Pony Express, whatever you like. And there are 9 things listed on it, which I'm going to talk about one at a time. The visual assessment is a description, moisture content, and it gives you the % water and the % solids. Soluble salts, which is also known as electrical conductivity, inorganic nitrogen, organic matter, and once we have organic matter, because there's a consistent relationship between carbon and organic matter, we give you the organic carbon content. The total Kaldol nitrogen, that's a much bigger number than the inorganic nitrogen, so for practical purposes, the total Kaldol nitrogen is all the nitrogen. Once you have items 6 and 7, the organic carbon and the nitrogen, you can calculate a carbon to nitrogen ratio, which we heard about a great deal yesterday and seems to be, it's of great concern to some people and of no concern whatsoever to others, like everything. And number 9 is the maturity index, which also, I know Uta Krogman mentioned this Solvita maturity index. We do use that product from Woods End Laboratories, and I'm going to talk about that a little bit more too. So, some compost comes into our laboratory, however it gets there, and on the upper left in that tray is basically the compost as delivered, okay? That's the whole thing. And it's in a porcelain tray. We try to make sure that we are not adding any contaminants to it before we analyze them. And the visual assessment that I made of this product here is that this is dark brown organic material with approximately 60% woody coarse fragments by volume. So why do I tell you by volume and not by weight? You'll see in the beakers on the lower left that on the left is the woody stuff that does not go through that sieve. And on the right is the finer material that is more consistent with what the average person would call compost. This is the finished stuff, all right? And the stuff on the left looks more like mulch. And we've certainly found that for the home gardener, for the gardening market, which is a large chunk of the concerns of the residents of New Jersey, they don't want to get mulch because they're going to mix this in with their soil. They're using it as a soil amendment. And they know that they have this woody material. It may create a problem with fungus. It may create any number of problems in a garden setting. It's good in a composting setting because it's a bulking agent. It can act as a biofilter. It can help avoid the loss of nitrogen. But there's a screening process. And when I make compost at home, I screen my compost. So the stuff on the left goes back in the pile and gets another chance to become compost next year. So anyway, we tell people how much there is. Because if you buy a truckload of the stuff, that's how it arrives. And this is your only chance to find out. If you're just looking at the laboratory analysis and you're not looking at the sample, you will otherwise have no idea of how much of the material is woody and how much is the fine fraction. Okay, I also need to say what I mean by compost, because this came up a few times yesterday. We have feedstocks, which several people mentioned, and we have compost, which I consider the end result of this controlled process of aerobic decomposition. So by analogy, the ingredients, flour and yeast and water and salt, you can make a loaf of bread from it, and many of us have done that, but they're not the same thing. But I'm going to tell you, if I took that flour and yeast and stuff to the laboratory and ground it all up, it might show exactly the same on a chemical analysis as the loaf of bread. It's got the same ingredients in it, okay? So, but there's still a difference between a loaf of bread and the ingredients to make a loaf of bread, and regular people can see that difference and appreciate it right away. You add energy, you add skill, you add technology, you add heat, you add time, and then you produce a loaf of bread. And the same thing happens with respect to compost. So on the lower left there, what I'm looking at there is quite a few wood shavings and 2 horse droppings. And I can see those distinct little horse droppings right in there. They're the round brown things, okay? Now, this sample arrived in a Ziploc bag to our laboratory with a label on it that said compost. Now, I can't stop you from calling that compost, but I wouldn't call it compost. I would call it stuff that may grow up to become compost someday, all right? Those are feedstocks. And the product on the right is the end result of this process. Now, of course, there is some kind of medium space between feedstocks and compost where it's a little harder to draw the line. But at the ends of the continuum, the differences are pretty clear, okay? So in the middle, you have immature compost, or you have compost that's in the process of becoming more mature, okay? Compost, basically, you don't recognize what the ingredients used to be. Moisture content. This, the silver thing in the upper left here is a scale. And I don't know if you can read the number on it, but there's a little porcelain empty dish, and we know how much it weighs because I weighed it. And the moisture content is determined on the basis of that whole sample. The way the sample comes into the lab in the baggie, I make sure it's mixed properly. I stick my hand in and go bump, and I put it into that porcelain dish. That's how it gets there. So then we weigh the dish with the moist compost, and now we know how much does this moist compost weigh. And later on, we're going to pop it in the oven overnight or maybe for 2 days until it stops losing weight, basically, is the technical way to say that. And it's at 105 degrees Celsius, so it takes, you know, it takes as long as it takes. Depends on how wet it is. Depends on the nature of the compost is the bottom line. We need this in part just because some people want to know. We want to know what is the eventual percentage of solids. If you're going to mix and make a soil blend, you need to know this because if you're shooting for some target of % organic matter in your final product, that's only done on a dry basis, on a dry weight basis. So you need to know how much of this wet stuff, which is the stuff that you're actually mixing, that came in the truck, how much of this wet stuff do I need to mix in to get a dry mass of whatever I'm interested in. Also, there's a few specific dilutions where we actually need the moisture content. So that's how it's done. And in the lower right is the little dish in the oven in the process of losing water. Now in the upper left, we've got the dry dish. And there it is, and it has lost quite a bit of weight. And so by the miracle of subtraction and arithmetic, we can discover that the compost moist used to weigh 67.1 grams. And that's partitioned into water and solids, and we've done the calculation. It's not unusual for it to be about 50-50 or so. This is maybe a little drier than average, and some of it is very dry, but mostly not. Mostly compost comes into the lab in a moist condition. But the important thing you need to know for later is that now I have that stuff in that dish, and it's quite dry. So I'm going to sieve it again through a smaller screen, the 2mm screen. And I've done that and made it into those 2 little piles over there. The coarse stuff goes in the discard pile. And the fine stuff is what we use for total Kjeldahl nitrogen and for loss on ignition organic matter. Okay? So we've just taken a fair amount of that stuff and discarded it. All right? When you read those numbers, you need to know, or you may need to know, which fraction of this material are those numbers based on. One intermediary step that leads to a lot of analyses is called a saturated media extract. And before we can extract the saturated media, we have to saturate it. And so this is a picture of how we do that. Basically, I take this 600 ml beaker and I fill it with compost. And then I take distilled and deionized water and I start filling in the cracks between the compost particles with water while I'm mixing. And that's just a plastic stirring rod sticking out of there. And this takes a little bit of time and a little bit of experience, because if you've had any experience with compost, you know it doesn't really wet up all that quickly. And so you add water and you stir it, and then you go away for a little while and you say, wow, it soaked up all of that water. I'm going to add a little bit more. And you stir it, and then you go do something else and come back and observe it again. So this is sort of an iterative process. And eventually you get to the point where you feel that you have gotten saturation and it's no longer changing. So now it's thoroughly wetted, and if you add more water, you're going to start to see water sort of ponding, puddling on it. We do not want free water. And this is just a way to test compost and to test potting mix is also done in a similar way. In terms of how much water to how much dry material there is, it really varies quite a bit depending on the characteristics of the individual compost. Things that are extremely decomposed colloidal material may take up a little bit more water per dry mass than other types. So again, it is kind of done with experience and repeated observations over the course of a day. Once it gets to saturation, it sits there and the water has a chance to work its magic and extract whatever it extracts. In the pH step, which is one of the many things on the report, we measured with a probe directly into that saturated medium. And basically, I take the stirring rod and I make a little well down into the center of it and stick the probe in there. A little tiny bit of water will accumulate, and I just need a little tiny bit of liquidy looking water. You can't actually measure the pH of a solid. So I right down into the center with the probe and get a pH reading from there. Typically, finished municipal, like leaf compost, will end up at a pH of about 7. Animal manure composts are typically a bit higher than that, in part because manure tends to have a higher pH than 7. So again, it's all about the feedstocks. Okay, if it's extremely high, that's a little different. But you know, depending on your system and what you're going to use this material for, you may or may not be all that concerned about the pH in terms of compost as a product. This is probably old news to a great many of you, even if you haven't seen it in a while. But I just want to know, before we start talking about pH and P this and P that, okay, these are terms that have definitions. They're thermodynamic relationships. The Ka is a dissociation constant. I'm going to come back to this because we're going to talk about nitrogen and ammonia soon. So the pKa is defined as the concentration of the products multiplied over the concentration of the reactant, basically. And for pure water, the pH, you know, we need an H before we get a pH, okay? So that we have the concentration of the H plus, and the pH is just the negative logarithm of that, because it's a less cumbersome number. For ammonia, it just happens to be that the Ka of ammonia, that's the equation. And for ammonium, which is the ion, I have a number. It's a thermodynamic constant. You look it up in tables. You don't have to figure it out at any point. And that number, 5.89 times 10 to the minus 10, could also be written as this decimal with a great many zeros. And basically, the reason that we use the pKa is that 9.23 is a whole lot easier to remember and think about than 0.00000 whatever 589. Okay, so think about the pKa of ammonium being 9.23, and hold that in your minds. So who cares about pH? We were talking about pH before. You care a little bit about pH because the pH has to do with what happens to ammonia nitrogen in your system. And very generally, there's ammonia gas in the air, and it will dissolve into water. And that's what those arrows are doing. There's some relationship. Okay? If you apply pressure to the gas, more goes into the liquid. Once it's in the liquid, that NH3 ammonia, it's quite toxic, actually, to your plants, and it's toxic to fish. It's not something you want a heck of a lot of in a biological system, but it will react with water. And basically, it takes that water next to it, and it yanks off a hydrogen and becomes NH4 ammonium, which is not nearly as toxic. And when it robs the water molecule of its H, it leaves OH. So what just happened? The pH got higher. Okay? If we add a whole lot of acid to this system, we add a whole lot of H pluses, then we're pushing the reaction in one direction or another. Everything we do to manage it pushes the reaction in one direction or another. And again, these are just the laws of thermodynamics and chemistry. It's not something that I figured out. This is stuff I look up. But these are relationships that hold like gravity holds. You know, they're not negotiable. It's not like maybe this happens. This is going on all the time. And the water that we have in our compost does not exist in a pool like a bathtub like this. The way it exists is actually thin films. They're coating your particles. And that's how water exists in soil, too. So the bottom line is, the end of the story, in the pH, at real high pH, we've got a lot more ammonia. Okay? And when we have more ammonia, more of it comes out of that liquid and into the atmosphere. But it doesn't just sit there because we have wind. And so the wind takes the ammonia away and it goes to your neighbor and it smells bad and they hate you. Okay? So that's why we care about pH. Okay? And on the right-hand side, let's imagine we have a plant or a bacterium that can actually use ammonia as a nutrient and say, I'm going to make proteins out of that sucker because I see some nitrogen in there and I want it. Okay? So if that happens and there's no NH4 over there, that pulls the reaction in that direction. All right? And because we care about ammonia, we care about ammonium, we care about nitrate, we care about nitrogen. As agronomists, we care about this. As natural resource managers, we care about this. So it's all about the nitrogen cycle and conservation to some of us. And to others of us, it's all about, does it smell bad? Okay? There's a reason that people use all that woody stuff in their compost. It's because it helps it not smell bad. You know? That extra carbon helps to combine with that extra nitrogen and make sure that the neighbors don't hate you. And that's important too. Back to the saturated medium. So we've got this saturated goo. And the way we make a saturated media extract is I have this, to the left, this white Buchner funnel and a vacuum flask. And in the center picture, it just shows you that there's little tiny holes in that funnel. And there's a piece of filter paper that we cover up the holes with. And that's a rubber stopper. So we make the whole assembly, and we apply a vacuum, and we pull that water out. And we have to pull it out. It will not drain by gravity because it's not free to move. That's the whole point of the saturated media extract. If it were more than saturated, water would drip out, but it's not. So I would say that more or less, there's about 2 times the amount of water in there as there is solids. But it might be 3 times, or it might be 1.7 times. It varies, okay? But it's somewhere in the neighborhood of maybe 1.5 to 3 times as much water by mass as solids, okay? And the liquid that's collecting down there in the lower right is our saturated media extract, SME. And we do a number of tests on that stuff. And here they are. So there it is, that liquid. And you know, we had a 600 ml saturated beaker full of stuff, and we only got about 50 milliliters of this saturated media extract. And that was after extracting it with a vacuum for 2 hours. So that's what it takes to get that water out of there. So now we have it. We're going to measure soluble salts on that. We're going to measure inorganic nitrogen on it. And sometimes we're going to measure available nutrients. And they're available. We know they're available because they drained out in the water. Okay? That's different from the nutrients where we have to ash and dissolve everything in acid. Soluble salts is also electrical conductivity. Dissolved materials, ionic materials in water, make the water better able to conduct electricity. Absolutely pure water does not really conduct electricity. So that's how we measure it. We try to make electricity move through the solution and get an estimate of the soluble salts by that means. It's measured with a conductivity meter. And again, we just stick the probe in there. We've calibrated the thing. And conductivity, the units are a little peculiar, so I'll mention them just so in case you see them written down, you'll know what that means. You've probably heard of the resistor, which is a measure of how electricity isn't going to flow through something. And the unit of resistance is ohms. So some genius decided that the mho, M-H-O, would make a good inverse to the ohm, O-H-M. And that's where that unit came from. So when I tell you that, you know, I'm going to report your conductivity in millimhos per centimeter, that really doesn't mean squat to most people. And again, mostly you don't care because you've got your specification, your sheet, and it said it's got to be between this, and who gives a rat dropping what the units are. Okay, they are what they are. But that's where that comes from. The SI system, the International System of Scientific Units, the mho has gone to the retirement home for units, and it's now called the Siemens for S for Siemens. So it used to be called the mho. And we still use mhos in our soil testing laboratory. So you'll get millimhos per centimeter. It will be your units. Notice that there is, I've taken the electrical conductivity of this saturated media extract. The conductivity doesn't care which ions are in there. It could be ammonium, it could be nitrate, it could be sodium, it could be potassium, it could be calcium. It's not discriminating. It's just telling you the total, sum total of the ionic species in there, and that's what we're reporting. There is also, in addition to the saturated media way of getting salts, there's the 1:5 dilution method. Some people ask for that specifically. Here's the method, and you basically have to get your moisture content first so that you get a dry mass, and then you use a mass of 5 grams of water for every 1 gram of dry mass of your material. So it's a little bit less sort of professional expertise, but whether the information is more useful, I'm not so sure. I do have a concern about it in terms of if you change from the old method, the saturated media method, to the 1:5 method, you're going to say, gee whiz, we used to have electrical conductivity or salts level of like 4 millimhos per centimeter, and now it's only 2. You know, we must have changed our process. Something must have happened. But actually, that's just an artifact that now you're using a different method for getting at the soluble salt. So you have to watch out for that. And if you have been receiving reports for a long time and you notice a change like that, check your units and check your methods, because you don't want to be misled just by a change in extraction methodology. There's not much to say about inorganic nitrogen except that ammonium is the NH4 molecule, and I probably use all these terms interchangeably without noticing it, so I apologize for that. It would be ammonium nitrogen or ammonium or NH4-N or NH4+. I would probably use all those things interchangeably. Same thing with nitrate, NO3 minus, NO3N, nitrate, nitrogen, they're all the same thing. We test this on this instrument. It's called an autoanalyzer, and it's got all of this linked stuff linked with a computer together. It's got chemicals, basic laboratory stuff. Nitrate and ammonium nitrogen are both measured on that instrument, so that you know, often it has to be diluted. We have our saturated media extract. Sometimes I run it full strength, and over on the right-hand side is a standard curve. So we take dry chemicals and weigh them out and get exact numbers, and for every time we measure this stuff, we have a standard curve. So this is parts per million, 1, 2, 5, 10, 15, and 20. Whatever I got to do to make my sample read someplace in that range between 1 and 20 is what I do. So maybe I have to dilute it by a factor of 10 or 100 or 1,000, and I can't figure it out ahead of time. It's a total guesswork, it's trial and error, and I win when my sample reads in the middle of that curve someplace and I can stick a number on it. And on the lower left there with this red color is what ultimately happens with the nitrate analysis. And that, I said this is like the holy grail of wet chemistry, is that you want to make your product into something that changes color so that you can detect it with a visual detector and link it up to your computer, and then everything is beautiful. Organic matter is done. I showed you previously the dry compost, coarse material removed. And now on the right we have that quartz crucible. It's actually made of pure quartz, and it has to be because we're going to put it into an oven where the temperatures are mighty high. We determine the organic matter by what we call the loss on ignition organic matter method, and that means we lose weight when all of the carbon is burned off into the atmosphere and leaves our system. And then we cool it down and we weigh that crucible. Again, it's a before and after weighing. And whatever weight we lost must have been the organic matter because it's gone. And whatever's left is ash. That's why, when we have big wood chips and stuff like that, that's not going to work. That stuff has to come out because I can't grind it in the mortar and pestle. Over here on the lower left is our muffle furnace, and that's the interior of the muffle furnace. Total Kaldol nitrogen. We also use this mortar and pestle again, and it's even more important because we're using very small samples. 1/10 of a gram, or maybe 2/10 of a gram, and again, it depends on our opinion of like how much is really in there. We kind of look at it and make a decision based on that. We put it in test tubes with concentrated sulfuric acid. We boil it in that heater block there at 375 degrees Celsius for several hours. So it's really a drastic process. What we have to do is destroy all of the organic material, and the nitrogen that's in the organic material has to be converted to ammonium, and that's what we're doing. So those are drastic reagent conditions, and that's what it takes to destroy all that stuff and convert it to ammonium. And we use the same setup here, the autoanalyzer, with a little different chemistry and sort of different concentrations. When we're done cooking those, we dilute it up to that little white line that's etched on the tubes to 50 milliliters. So we know how many grams there were, we know what the volume is, and we can come up with a percent by weight. That's how it's done. Total Kaldol nitrogen. Kaldol's undoubtedly some chemist. And now that we've come up with a carbon and a nitrogen, this is pretty straightforward. I wrote it down for you. The maturity index, a couple people expressed interest in this. Again, we sieve, depending on the compost, if there's a lot of woody stuff in it, because not much happens on the woody stuff. That's relatively inert. So what we really want to know is what's the biological activity in here, what's going on. So this is not done on the whole compost as received, unless it's a pretty fine compost. Through a 1/4 inch, and it goes to this little reaction jar there. So this is the Solvita test from Woods End Laboratories, and there's our colorimetric paddles. We measure carbon dioxide evolved into the headspace of that jar, and ammonia also evolved into that headspace. The little paddle changes color based on our 4-hour incubation, and this has been calibrated and well documented in the literature, so we're comfortable using somebody else's prepackaged kits, and we don't have to become experts at compost maturity ourselves to do this. They provide this colorimetric chart so that if you were to do this yourself, which it is possible to do this yourself, you can compare the color of the paddle to the little color chips there and come up with an estimate of where you are with respect to your compost maturity. We use a digital reader that's shown over there on the lower right, and it's certainly more accurate. It's required if you're going to make a quantitative assessment of how many parts per million of carbon or something did you come up with, because you only get whole numbers, if you're using these color chips, it's like 1, 2, 3, 4, 5, 6, 7, whatever. With the reader, I can get like 4.26. And a little more exact, and also I don't have to be so confident in my own ability to assess paint colors, because I know perfectly well that I'm really bad at it. So the maturity index, this chart here is from the Woods End Laboratories interpretive materials, and we get an index and also an interpretation which tells us what is this material good for at this level of maturity, or else what are its management needs. So like how many times a day are you going to have to turn this in order to keep it well aerated. So I think this is a really useful addition to a compost test. Mostly we don't get any color change on these ammonia paddles. And I think that's because people who are making compost have at least learned one thing, is that they are in big trouble if anything smells, and that if you load it up with extra carbon, it's going to help prevent that. And so we're just, you know, it's very unusual for us to get a compost that actually even registers. Additional tests that some people get and most people don't, but they're available, are available nutrients, which are run on that saturated media extract that I talked about at some length. The analysis is performed on a snazzy, expensive instrument, the atomic emission inductively coupled plasma spectrometer. You probably don't have one, but we do. And so here's one. I took this from a report where somebody decided that they did need available nutrients. And again, available means they're soluble, they're leached out with water, and might, in theory, be available to a plant, you know, in the current growing season. This is a contrast with conventional soil testing, where the nutrients are not extracted by water. They're extracted by sort of a cocktail of different chemicals and are intended to tell us the amount of nutrients that your plant is going to get out of that soil sample over an entire growing season. Okay? So that's for soil, this is for compost, and this is a water extract. And down at the bottom, I simply mention, because we occasionally do this, that total nutrients can be determined. I don't know why people ask for them. Maybe they're researchers, maybe they're just curious, or if they've got too much money and they don't know what to do with it. But total nutrients, we ash the sample in the muffle furnace, dissolve the ash in acid, and run it through the same instrument, and we come up with numbers which are going to be higher, because whatever's total is going to be more than what is extracted with water. Okay, the take-home message. There's not all that much of our testing that is done on the entire sample as it comes in the bag, which would also be the entire sample as delivered to your site on a truck. Okay? It's fractionated, and it has to be for the purposes of analysis. So different tests are done on different parts of it, and I have just attempted to tell you how that works. Representative sampling is really important. And so your data are only good as your representative sampling, which begins with the person who gets the sample from the windrow or from the compost pile. So don't send the worst slacker that you employ to do that task. It's just because you get dirty doesn't mean it's not important. The visual assessment that we have, we started to include that because we think it provides information that's not available anyplace else on a test report. And we felt that our customers want that and need that. Somebody who's producing a compost wants to be able to say, you know, look what's here or is not here. Sometimes I'll say, and bits of plastic and, you know, anthropogenic material. Or I could say, there is no anthropogenic material in here. And I've been asked to make a point of mentioning that, and I'll do that. You know, if I see bits of glass or bits of plastic, though, that's relevant information. People do want to know that, and they should know it. And different situations exist, different feedstocks, different composts, different end uses, different clientele needs. There's our website. There's some interpretive stuff, some facts on there, and our director is Stephanie Murphy. She knows everything. Questions? Sir?
You talked about the difference between leachable and total nutrients. 40-year compost maniac, one of the things I like most about compost, and there are many, is that I can go ripshit with it 1 year and slack off totally for a year or 2 or 3 after that. And we're dealing with total nutrient because there's fungi and so forth in there that have very powerful microlocation acids to dissolve mineral nutrients in my compost that aren't available to your leach test, and therefore they're also not available to a rainstorm to wash them out and leave my garden with no food.
Well, that's exactly it.
That's what
if you think of compost as a fertilizer, it's a slow-release fertilizer. So ultimately, you can get everything that's in the total nutrients, but it may take 40 years. You know, it may take a long time for whatever organisms and processes in your system to totally digest that compost so that nothing is left but the minerals that don't go into the atmosphere. So, anybody else? Yes, sir?
Is there any other parameters you would test for with manure or food waste that you wouldn't test for with just vegetative material?
Like pathogens and stuff like that. I know that a lot of people are awfully concerned with pathogens. Not my department, though, so I can't really tell you. Yes?
If you're doing manure compost, which is one of the things that I do, you need to do a E. coli and salmonella test. And if you don't reach your temperatures, you're not going to kill off the E. coli and salmonella. So those are two big, important tests that you want to do with a manure-based compost.
Yeah.
How much does it cost to run
The technical compost battery is $125. Yes, sir.
You mentioned the Solvita test. Do you run it? Do you do that?
Yes, we do. It's part of our technical compost battery.
And that would be something a producer could do themselves, a composter could do themselves as a field check.
You can go to Woods End and buy their kits. You know, if the digital reader is kind of pricey, so probably an individual wouldn't want to buy that. But if your needs are not extremely quantitative, you can do that yourself. I'm done. Thank you.